Forum. So I just want to say I'm very proud to be here and to welcome you all to the first Knowledge Forum. Okay, thank you very much.
Thank you very much.
Thank you very much, Consul. Gaya ng sinabi ni Consul, hindi ako nerdy-nerdy. Gusto ko yung science, kaso hindi niya ako gusto. So, nakakatuwa naman, puro matatalino pala nandito. Kasi yung mga kapatid ko yan, mga nag-aaral din sa, ayan, si Aletea sa Quezon City Science, yung isa kong kapatid sa Philippine Science. Ako science, hindi ako nakapasa. Science! Yun. Kaya ito trabaho ko. Kaya ako naging broadcast, whatever. Yan. So, nakaka-ingit naman kayo. Pakilala ko na yung una nating speaker. Ang una po nating speaker ay Civil Engineering graduate from UP Diliman. And, ako, ang bigatin pala ito. He got his PhD from University of Tokyo. Ang sosyal naman ni Sir. And now, he is specially appointed Assistant Professor for the Research Institute for Natural Hazards and Disaster Recovery from Niigata. Tinanong ko na, Niigata. Oh, okay, sorry Niigata University. At ang pag-uusapan po natin ngayong hapon, Science and Technology Inventions. Kunyari, interesado ako. Super computers daw ang ipapakilala sa atin ni Professor. Tungkol daw ito sa mga urban earthquake analysis. Yan. Kunyari, alam ko itong mga to. Yan. Pero para ipaliwanag sa atin kung ano nga ba itong mga supercomputers na may kinalaman sa earthquakes, dahil hindi lang naman Japan ang may problema nito, I think dahil nag-mature na ang mga faults somewhere, sa lahat, sa buong mundo yata, may mga faults. So, this is everybody's concern. May we now call on Professor Pher Errol Quinay. Tama ba? Palakpakan niyo naman si Sir.
First, I would like to thank staff for inviting me over. Dapat attend lang ako okay, my talk will be on development of fault structure simulation for seismic analysis. So,
Mic po.
sorry, this is so I think from the title you already understand it's about urban area and earthquake analysis, and probably I will expound my presentation on fault structure simulation. So I'm currently working in Niigata University. Okay, I place here two pictures. This is a picture of a typical urban area. And this is actually in Niigata, and showing the buildings and regular structures. And this is in Japanese literature. It's a very well-known character. His name is Namazu, and it's a catfish. And whenever Namazu moves, they say that the earth moves, so that's the ground motion part. So whenever you encounter some maybe websites related to earthquakes here in Japan, you can see something like a catfish as a mask. How do I do this? First, review of related literature. Anyway, these are the past earthquakes happened in Niigata, and these three are probably some of the well-known earthquakes that happened in Japan. And this is in Niigata Prefecture. 1964 7.5 earthquake, 2004, already 10 years have passed since this earthquake, and 2007. 6.6 magnitude. So, why are these very important in the case of Japanese design of structures? Okay, first, the 1964 earthquake caused a severe ground deformation in coastal areas in part of Niigata. And as you can see here, probably you have seen this picture before. These are apartment buildings, and the ground to support these buildings suddenly lost some shear strength. They call it shear strength. So what happened is that the ground subsided, and we call it like liquefied. And these structures are actually structurally sound, so there are no problems with the structural part, except that the bottom part got damaged. Now the second one is 2004 earthquake. It's very for researchers. This is very well known because many landslides happened in mountainous regions. However, for the public, it's more well known with the first event where the Shinkansen got derailed. So in like 30 years of history, 30 plus years of history of the Shinkansen, got derailed because of that earthquake. And the 2007 earthquake caused a lot of ground deformation. And this is very important in the design of nuclear or critical structures, because at that area, there was a nuclear power plant, and until this day, the issue whether some radioactive elements were released is still unknown, because the current issue of the Fukushima disaster overshadowed this issue. But still, the issue is still not resolved up to this day. Okay, let me talk about the existing major faults in my area. So this is where I live, and so this is a website. You can publicly, the availability of the information regarding major faults are publicly available in this web. So you can see they're quite interesting in the future. So probably it's more interesting to see the case of Tokyo. So you're somewhere here, and these are the major faults. And well, this part of Saitama already have some fault. These are major faults. I didn't include here what we call subduction zone areas. The magnitude 9 earthquake happened several years ago. The subduction zone area. And they're expecting another one, very strong one, at the southern part actually, that will probably cause a lot of damage in Shizuoka. We call it the Nankai Trough earthquake. In the current scientific, many scientific papers are now being published studying the area around here. That's the what we call M8 class, magnitude 8 or higher class earthquakes. The one we experienced will be experienced in Tokyo, probably around 7, the maximum. But this is already, since it's very overpopulated, so the losses, I think, will be very high in that case. So whenever someone meets me and know that I'm working on civil earthquake engineering stuff, these are the top 3 that's always asked of me. So when's the next earthquake? When's the next earthquake? And after that, where? And then is my building safe? So the problem is, this is the most the most asked question, but it's the most difficult to answer. Certainly because what the person asking is pertaining to is the major earthquake, a large earthquake, which happens every 100 or 150 years, which is kind of long. It's a geologic length, geologic time scale. So this is, if I answer like 150 years from now, I think it will not satisfy the person. But that's not actually the true scenario. The where is probably we can go back to the previous slide. So now every one of us can check what's the nearest fault to us. But it is I can see that there's still so many faults that have not been mapped, and some faults are still being generated at this time. So that's for the second question. The third question is more related to the engineering, because in the design of structures, materials and design are measured, and uncertainties are also included in the design procedure. However, for extreme events, for example, magnitude 8 or above earthquakes, and we need to recheck our buildings for safety. Okay, so my study is on fault structure simulation. That means that I'm working on the available fault information. Fault information such as magnitude and how big the fault is, to predict the response of structures somewhere. So you can see here it's, I think it's the natural way of modeling by way of the physics. And this is physics-based wave, seismic wave propagation, or wave propagation modeling. Traversing different medium with different soil property. So that's actually like the science explanation for that one. And if we take a step back and look at what field this problem is included, it's seismology, because we need to understand the physics of earthquakes. But still, it's in infancy, because the large earthquakes are very rare. And it's a problem of engineering, civil engineering, and mechanical engineering, because there is a problem of safety and serviceability and cost involved. And since we are solving from fault process, wave propagation, amplification in basins such as Kanto region, the computation is very large.